Hi, welcome to the Ask IITians video lecture of Functions and Logarithm. My name is Sunil Kumar. I am a graduate from IIT Kharagpur and have been associated with the Ask IITians as an in-house faculty for mathematics. In this chapter of Functions and Logarithm, we will look at various topics including the basic definition of both the topics, and then in functions we will start with the various types of functions that we have. Then we'll move on to the number of functions of various types along with composite functions, inverse of a function, many-one function, one-one functions and periodic functions and different varieties of functions like these. Along with that, we'll learn the importance of the curves along with the functions associated. And then in the next part, when we come to logarithms, we'll again go through the basic definition of logarithm and then continue on with the operations including logarithm in the modern mathematics. Now in this part 1, we'll look at the basic definition of functions and then types of functions that we have. So let's move on to the lecture and study it.
Hello, my name is Sunil Kumar. I'm a graduate from IIT Kharagpur and an in-house expert for mathematics in Ask IITians. In this chapter, we'll be studying functions and logarithm. Now, up till now, what do we know? Till now, you must have studied so many variables with constants in chapters like linear equation, quadratic equation, and in different forms of algebra. Now, the composition of variables with constants give us a unique feature. With the different outputs that we get, there are invariable different number of inputs that we actually provide. Now based on these inputs, the outputs that we get, it goes through a certain process which we name it as a function. Everything that you have studied in linear equation as well as quadratic equation, other equations involving variables are a part of function. Now, how do we differentiate functions is what we are going to study. What is the strength of a function? We are going to study. And what could be the limit of a function. In this chapter, we are going to understand the functionality of a function. Now, this is just, have a look at this diagram that I have drawn. This diagram is the best example to explain a function. Alright. So you see, in this part, I have a machine. Okay. This machine tells me this is the machine that tells me what I'll get. Okay. Based on that, what is the requirement? I process it through here. Then it goes. These are my inputs. Everything goes in there. The machine runs is processed, and in the output, I get these things. Now this is all that we are going to study. Okay. So basically, a function is something that tells us what is the processing of any numerical equation that involves constant as well as variables. Now, let's look at the contents that we are going to study. Okay. First of all, we'll have a brief introduction about functions. Then we'll be studying domain, codomain, and range. Important types of functions that we have: equal and identical functions, classification of functions, number of functions of various types, composite functions, odd and even functions, as well as inverse of a function, periodic function, and some graphical transformation. Now, all these come within the part of a function. Now, you must be a little confused that functions contain so many topics. Yes, it does. Till now, everything that we have studied, let's say, you have studied linear equation of two variables, right? Let's say it is 3x plus 4y is equals to 5. You see, based on the number of variables, my function is defined. Okay? This is a function of two variables. Then I represent my function in this way. This f signifies function, and these two are the driving forces or the processing forces, also known as the variables of the function. Okay, mostly we will be dealing with one variables over here. So I represent my function like this. Let's say 4x cubed minus 3x plus 7. So this is a function of one variable. Now also you need to be sure that I represent this f over here, but it doesn't always have to be f. F is just a prototype. Okay, it can be anything. I can also write this same function using gx. After all, in variables, that is the advantage that we get. We can use any variable anywhere. Alright, so this is just the naming part. Okay, so this is how we are going to be studying. Now let's look at what a function is. Now first of all, let there be A and B, two non-empty sets, okay, having m and n elements respectively. Then the number of relations possible from A to B is 2 to the power mn, right? Out of these 2 to the power mn relations, some are called functions, also known as mapping from A to B, providing following two conditions hold. Now what are those two conditions? First, all the elements of A are associated with the elements of B, the most important one. Next, each element of A is associated to one and only one element in B, that is, no element of A is associated to two or more elements in B. So basically what it means, through a process there has to come only one output from one particular input. Okay, there cannot be two different outputs from one input. And all the elements, basically, since we are putting an input, there has to be an output, right? So this first part signifies that. And the second part, as I explained, for one input there has to be only one output. There cannot be more than one output for a particular input. You have already studied about sets, right? So basically in functions what we do, we collect everything together, okay, then we first differentiate using sets. Okay, that is the reason why we studied sets. So after we studied sets, what we do is I differentiate it, or I tag them in different categories, or I build different subsets so that I can define everything very easily. Now let's look at the next part. Graphical method is a very important and the most interesting part of functions. Every functions, as you have just seen, okay, let's say you have again x plus y is equals to 3. You have studied this in linear equation of two variables, right? Now if you plot this on a graph sheet, let's say like this, you will get something of a line, right? So everything that you draw, every function that you write, any function, it has to be represented, or it is represented on a graph sheet, and they will have an existence there. It can be drawn in a graph sheet. It can be anything. It might look like this, okay, or it might just look like this, but every function, any variable plus constant combination can be put in a graph sheet. Okay, what do we do with that? We basically need to check whether a relation between x and y is a function or not. Okay, how do we do that? We draw a line parallel to y axis, and if it interests the graph at one and only one point, then the given relation represents the function. Okay, so basically what we do is we correlate the x and y graph, and we see whether or not the given value for the given input is true or not. Okay. Now, how do we basically do it? Let's see. You see, these are the two different examples that I'll have. What I did is I drew a parallel line, okay, to y-axis over here, okay, and then the graph I need to draw. This is my graph. This is my fx, okay, which is equals to my y here. Alright. When I draw this graph needs to cut this y-axis at only one point. Then the given relation between the function is true. Okay. So you see over here, it cuts at this point, right? So this is my function. Why is that? Unique value for every element in A to every element in B. Now over here you see it is cutting at two different points. Okay, so for one f of this is my function of y. You see, x equals to y square, fy is equals to y square. This is the function over here. What it does is for one variable it has two different values, or for one input it has got two different values. So in that case this will not be a function and this will be a function. Now the important assets of a function are domain, codomain and range. Everything will be governed based on these three parameters. From now onwards to everything you studied in a function will be governed by these three factors. Now, what does domain, codomain and range signify? You might also think that these three are very similar things, right? But there are narrow but important differences in each of them. Now, let there be a function, okay, from A to B. Then set A is called the domain of F and set B is called the codomain of F. Alright. The set of all those elements of B which are related by the elements of A is called the range of F, or the image of set A under the F, and it is denoted by F of A. So basically the inputs is what defines the domain, the outputs based on those inputs is what defines the codomain, okay, and the set of all those elements of B which are related by the elements of A is called the range. Okay, so that is all about the domain and range. So basically you need to understand for fx equals to x square, if x equals to 1 and x equals to 8, let's say a function this will exist only from here to here. So x equals to 1 and 8 will be the domain, and the values that I get based on that, that is 1 and 64, 1 to 64 becomes the codomain and the range. Okay. Now let's have a look at a different example. You see, I have A over here and this is my B, and this is the function that I am running. Now over here A and B, they give one value, okay, that is 1. So over here my domain of R7 is A and B, that is these two elements. Codomain is 1 and 2, that is these two values, and the range is just this value. Okay, so this is how we differentiate all three of them. Okay, so this is an example based on that. You see, have a look at again. All the elements in A is my domain, all the elements in my B becomes my codomain, and the outputs based on that is my range. Okay, now let's continue further. The same thing is significant over here. Now over here you will see that both my range and codomain are same. Okay. Now let's look at some important type of functions. First of all, let's start off with real function, the most important one, or the basic function. Now functions in which both domain and codomain are the subsets of R, that is the set of real numbers, it becomes a real function. Okay, like this. You see over here in this graph, everything is in this positive axis, right? So this becomes a real function. Basically all A and C will be, that is the domain over here, the domain lies in R. Alright, the domain of F is A and C, okay, and it lies in R. Codomain is also R and the range is U and W. Okay, so I think this will clarify all your doubts about domain, codomain and range. Now moving on, next function is a constant function. For any function from R to R, let it be a real function which can be defined as this, my fx equals to c for every x belonging in R. You see, this signifies for all, this signifies belongs, okay, in R, for some C that belongs in R. Okay, then you see the domain of F will be R, the codomain will also be R, and the range is the constant value that it is getting. Basically for this function, anything, any variable that is given, I'll get a constant value, a unique value, and it will remain the same throughout any input that I feed in. Okay, so then my domain, my codomain and my range changes. Now you see, this is an example of a constant function, okay, where my y is equals to some value over here. Now important point to note that for every constant value a that belongs in A, my f of a to b, that is my function a to b, is always a constant function. If c belongs in b, f of a equals to c for sum. Okay, now let's look at the next function. I have my identity function. It is just like a reflection on the mirror. Okay, I have my function fx equals to x, this signifies the identity function. In this case, for every, it will lie again from R to R with real function fx equals to x, x again belonging in R. Over here the domain is R, codomain is also R, range is also the R. Why? Whatever the input is, that is the output over here. That is the reason why we are having everything same. You see, any whatever you put the value of x, that will in the input, that is in the function, I'll get the same output. Okay, for every a belonging in A. Now what does this signify? This signifies the element of A. Okay, that I had A and B, right? So every element of A is represented like this. Okay, so for all a belonging in A, my f function is from A to A. It is given by f of a equals to A, is the identity denoted by IA. Keep this in mind because it will be used quite a lot of time. Okay, same as the identity relations. Now let's look at some standard real functions and their graphs. In this case, first of all, I have the modulus function. Very interesting. All the graphs illustrated over here are quite interesting. Now the modulus functions, its property is that it will again belong from R to R, and for this case I'll have two unique sets of values, that is for different x I'll get a different output. Okay, you know what a mod represents, right? So I'll have an x as well as a minus x for a different value, right? In this case, for every positive value, my x will be greater than or equal to 0, and every negative value, my x will be less than 0. Now over here the domain and codomain are the same. The range, this will now be interesting part. This is the first time you have a little complexity. You see in the range, it will be for an x where my x belongs in R. For all the x greater than or equal to 0, so it will be from 0 to infinity or undefined, as mod x is greater than or equal to 0. It will be a set of non-negative real numbers. So everything, no matter if you put x equals to minus 2, my f of x will be equal to 2, right? So no matter what the input is, the output will always be a positive. So this is the graph. You see, you put any input, even it will be negative. Okay, so you see x is in negative direction, but my y will always be in the positive direction. That is, my output will always be in the positive direction. And since this is already a positive, it will be in positive itself. Moving on to the next part, the greatest integer function. This is the bracket that signifies the greatest integer function. What is the greatest integer function? For any function from R to R, okay, greatest integer function is less than or equal to x. Okay, now how do I understand this more clearly? Let's say I have 2.1, okay, and I need to put it like this. Okay, so my 2.1 will becomes 2, that is the greatest integer function less than or equal. Okay, 2.1, in this case the greatest integer will be 2, which is less or equal. So it is less than 2.1, right? So this becomes my greatest integer function. Okay, now for this case, what is the lesser value? Minus 3, minus 2.1. So minus 3 will become the greatest integer function. Basically, we sum it to the nearest value, but which is lesser than the value itself. Okay. For 2, again 2. For 3, 9, it is 3. For minus 3.9, it will be minus 4. So the nearest value I need to close it to, but it has to be lesser than the value itself. So for greatest integer function of x, my 0, for all it will belong from 0 to 1, 1 from 1 to 2, and 2 from 2 to 3. Okay, and so on it goes. Now also I need to be sure that for negative conditions it has the condition like this. You see, for minus 1, lesser than value of minus 1 is minus 2, right? So it will move in the other direction, and so on. So this is the interpretation value for greatest integer function. Combining this, we get for, you see, everything can be plotted in the graph, I said, right? So you see, I put it in the graph, it will lie like this. You see, it is like a step. Okay, so for every, let's say there is some value over here, that is from maybe 1.9, so that will lie from at 1. Similarly at 2, for 3, so like this it goes on. Alright, now let's move ahead. Filled circle means the point is on the graph. Okay, you see, this is another example for that greatest integer function. Unfilled circle means the point is not on the graph. So in this case the domain is R, codomain is R, and the range is Z. Now let's move on to an interesting one. I have the exponential function. Okay, so basically I write the variable in the exponent form, so that is why we call it the exponential function. From here the function will run from R to R. Okay, and my f of x is written like a to the power x. A is my some constant. So over here again my x will belong in R, and a will always be greater than 0. Okay, a cannot be 1, a will be in R. So in this case a, you see where my a lies, from 0 to 1 union 1 to undefined, but it cannot be a negative. Let's take a look at the case 1. Let's say my a lies from 0 to 1. So let's say my a is equals to 1 by 2. Then y is equals to this. If I put, it can be written like this. So this is my function. Okay. So like this, if you look at the table for x and y for different values, I'll get these different variables or this different outputs. Now you see the graph for this. Every graph for every function, my exponential function graph, it is always like this. Now you see this is a significant point. Always this graph will keep on going like this, but it will never meet on the x-axis. Okay, we'll study this further detail. Okay, but this is the important point. Okay, for any exponential function, if a function goes like this, it will always be almost touching to the x-axis or the nearest axis, but it will never directly touch that. So it will form an asymptote. Okay, well, so in this case it comes close to the x-axis over here, but it will not touch the x-axis. Now that is the important part of the exponential function. Let's look at the case number 2. For every value greater than 1, let's say my a is equals to 2, then y is equals to 2 to the power x, right? So over here these are the values for every input that I have. You see my graph, it will look like this. You see over here again, it will almost touch the axis, but it will never do. It will always be some distance apart. Now for this case my function, it will be R, my codomain will also be R, but my range, it starts from 0 and it is not defined. So it will lie everywhere in the from 0 to positive direction. Let's take a special case. Let's say for a equals to e, which is greater than 1. Okay, this is my function of an exponent function. So in this case, how will the graph go? It will go like this. You know the value of e is greater than 1. So the function will go like this. Now, another important functions. We'll also be starting logarithms in this chapter. Okay, but what are logarithms? This is just a preview or a trailer for that part. Logarithm function is y is equals to log bx, some simplest form. Okay, you have studied logarithm little bit, right? So logarithm, in this case, how the function curve looks like is going to be important. But before that, let's look at the function. My function, let f lie from 0 to undefined. Okay, why? It is the same for exponent as well as logarithm. Why? Because you see, logarithm and exponents are like cousin brothers. Okay, so they will be similar but different, but they come from the same root. Okay, so let this function be from 0 to undefined, but it will belong in R with the real function. So my f of x can be written as log of bx. for every x will be greater than 0, and my b will also be greater than 0. B cannot be equal to 1. Why? Because the base cannot be 1 over here. Okay, it depends, varies from different cases, but it cannot be 1. That is for sure. B will also lie in R. So the domain for B is this one. Okay, now let's look at the case number 1. Let's say my B lies from 0 to 1. So in this case, these are my different values for different output. So if I plot the graph, it will look like this. Okay, moving on. Let's say if my B were greater than 1, these were my outputs, my graph will look like this. So in this case, my domain of f is equals to the codomain of f, which is equals to R, and my range will also be the same. Let's move on to the next part, which is called to be the equal functions. Why do we call it equal functions? Because the name suggests the real thing. The two functions f and g are said to be equal if and only if there is no error. This means if and only if. Two functions f and g are said to be equal if and only if the domain of f is equals to the domain of g, codomain of f is equals to the codomain of g, fx equals to gx for all x belonging in the domain of f or domain of g. If all these three conditions hold, then we can write the two functions are equal, that is f is equals to g. Alright. Now the types of functions that we have. Up till this now, those were different variations. Now comes the important part, the types of a function. For any function, what can be the different types? First and the most important one is one-one function, or also known as the injective function. What does it say? Any function from a to b is said to be one-one functions or injective if different elements of a have different images in b. That is, if AB belongs in A, then such that A is not equal to B, f of A is not equal to B. Thus, my f from A to B is 1 to 1 if and only if A is not equal to 0, f of A not equal to 0, and A and B belongs in A. Okay, so this is my 1-1 or injective function. Or if my f of A is equals to f of B, A has to be equal to B, and A and B has to lie in A. So that is 1-1 function. Next, let's have a look at its example. Now let there be function f a b. Okay, from 1 to 2 be the function given. Over here, let this be the plot. Okay, now in this case 2 and 3 are 1-1 functions. Let's look at the two. Why so? Now for each case over here, you see 2 and 3, they both have one unique value, right? A has 1, B has 2, A has 2, B has 1. So both of them have a unique value. A is not equals to B, so this is a 1-1 function. In 1, A is not equal to B, but f of A equals to f of B equals to 1. Doesn't satisfy the condition. In 4, A not equal to B, but f of A is equals to f of B, which is equals to 2. Does not satisfy the condition. Hence 1 and 2 are not 1-1 functions. To check your injectivity of a function, let the two functions fx equals to fy. If it gives x equals to y only, then f is one function. You see, in this case, if you compare both the functions and solve it, your x equals to y, this will be coming. Now, also I can have for x equals to y, f of x equals to f of y is true for all the functions based on the conditions, but its converse is true for one function. Okay, important selling point for this function. Okay, now the injectivity of a particular function can also be checked by its graph. How? If the lines parallel to x-axis cut fx in not more than 1 point, then fx is one function, that is fx is not one function if at least one line parallel to the x-axis cuts fx in more than 1 point. Okay, so in this way, if you plot it on a graph sheet, then if all the lines parallel to the x-axis cut the function point at not more than 1 point, that is, it will cut at least at 1 point. Okay, then fx is one function. Okay, now if and only if a belongs to b, this one function, then 0 of a always will be less than 0 of b. Now the alternative, if my f of 1 is equals to f of minus 1, but obviously a1 is not equals to minus 1, then in that case, using graph, you see it cuts a parallel point on the x-axis. Clearly, any line parallel to x-axis cuts fx at 2x only at 1 point, thus fx is 1. Okay, so these are all the parameters that you need to check before you need to confirm whether or not this function is a one function. Now, let's go ahead. You look at this graph sheet. Okay, what does this signify? Over here, my y is equals to 4 cuts y equals to x square in 2 points. Hence, my fx equals to x square is not 1. Okay. Also, in this case, the 2 points on fx. Okay. So again, not 1. Now, let's have a look at the example based on the topics that we have just discussed. Okay, we have already seen different examples. This is a one exercise question. Okay, let's have a look at the question. The question here says that f and h are in relation from a to b, where a is equals to a comma b comma c comma d and b is equals to s d u. Okay, now they are defined as follows. My f of a is equals to t, f of b is equals to s, f of c is equals to s. Like this, I have defined total 9 functions. Okay, now based on all these informations, I am being asked which one of the following statements is true. F and h are functions. F is a function, h is not a function. F and h are not a function, none of these. Okay. Now, if I look at the equation, how do I solve it? The first thing that we are going to do is, we'll have a look at the graph. Now, from this, I draw this. Okay, I draw the map for A and B. Okay, range and domain. From this, I gather that A has T, B, C have S, D has U. Now, what does this give me? Now, each element of A is associated to a unique element of B. Hence, F is a function. Okay, so I have got that option. Now, from these two, it can either be 1 or 2. Let's explore the other options. From this, I can get in the basis of for h function, this was for f function, this is for h function, I gathered this piece of information. What does this give me? That each element of A is associated to elements of B, but A belongs in A is associated to two elements of B, namely S and U, violating the second condition. Therefore, H is not a function. So, this will give me the option number B as the answer. So, I have F as a function, H is not a function. Why? Because it violates the second rule, which says A belongs in A is associated to two elements. You see, A has two elements over here, this one and this one, which cannot be true. Alright, so based on that, this will not be a function. Okay.
Alright, so that was the part 1 of the video lecture. Now in this, what did we learn? We learned the basic definition of a function, and then we went on to study different types of functions that we have. In the next part that is coming up in the part 2, we'll continue on with the types of functions, and then we will move on to the composite functions and the number of types of functions in various conditions. So stay tuned with askIITians for part 2.